Okay, so let's really get into how derivatives and integrals are related. Think about when we had the derivative of an amount. Well, we're finding the rate at which that amount is changing. And here's an example. If water is being drained from a swimming pool and R of t represents the amount of water at any given time, then R prime would represent the rate at which the amount of water is changing. So what would be the units of R prime? Well, if it's the amount of water in cubic feet, it would be cubic feet per time, hours. Rate of change. So it's a rate. So what happens if we take the integral of a rate? Well, we end up with the amount of change. So in this example, if we took the derivative of the rate at which the water is changing, then we're going to get the amount of water at the end minus the amount of water at the beginning. The overall change in the amount of water. So here we have velocity. It says approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum. So if we're going from 0 to 30 and we're going to be using a midpoint, then that means we have to have midpoints. So that means we're going to be going from here to here so that we have a midpoint for our height. Here to here, with this would be our midpoint of a height. And here to here, with this being the midpoint height. So the approximate value of the integral from 0 to 30 v of t dt equals, so this would be one rectangle, the width would be 10, and the height would be 1.6. The next one has a width of 10 and a height of 3.1, plus a width of 10, and we're going with a velocity as our height of 1.6. Oh, I should use squiggles. Approximation. Squiggles. So that gives me, oh, that's pretty easy, 16 plus 31 plus 16. That gives me 63. And so if we had velocity, which is feet per minute, times a certain amount of minutes, what are we getting back? Well, we're getting back feet. This would be the distance traveled from 0 to 30. What is the value of the integral from 5 to 25 of a of t? Wait, I don't have a of t, but wait, if I take the integral of acceleration, I'm going to be finding the change in velocity. So the integral of velocity finds the change in distance. The integral of acceleration finds the velocity at the end minus the velocity at the beginning. So v of 25 would be 1.6 and v of 5 was 1.5. So the overall is 0.1 using correct units. So velocity minus velocity, that's going to give me feet per minute, is the change in velocity from time 5 to 25. So here are some examples. We have water in a tub, modeled by a strictly increasing, that's good to know, twice differentiable function. Oh gosh, that means it's definitely continuous and differentiable and all that good stuff. Where WT is measured in degrees Fahrenheit and T is measured in minutes. Using the data in the table, estimate the value of the W prime of 12. So the change in temperature over the change in time around 12 minutes. So we'd be using these values right here. So we would be finding, we're finding the derivative of W at 12. We're going to have to estimate it by using the water temperature at 15 minutes minus the water temperature at 9 minutes divided by the change in time. So the change in water temperature over the change in time, that's 67.9 minus 61.8 divided by 6. And I get, this is approximately 1.017, 3 decimal places. And this is a rate. So this is the change in temperature, degrees Fahrenheit, per time, minutes. Interpret the meaning of this. Well, it's positive, and we knew it was increasing. So the temperature of the water is increasing at a rate of 1.017 degrees Fahrenheit per minute. Is it always increasing at that rate? No, just at time 12 minutes. Use the data in the table to evaluate the integral from 0 to 20 of the derivative of W prime. So if we're taking the integral W prime, that's going to give me back W, evaluated from 0 to 20. So when you take the integral of a rate, you're going to get the change in the amount. Going back to fundamental theorem of calculus. So W at 20, the temperature at 20 minutes was 71. The temperature at time 0 was 55. And I'm being lazy. I'm going to double check that. And I get 16 degrees Fahrenheit. Now what does that mean? The temperature of the water changed by 16 degrees Fahrenheit from time 0 to time 20 minutes. So after 20, from 20 to 25, the function W that models the water temperature has a first derivative given here. Based on this model, what is the temperature at time 25? Well, if they had given me W, I could find it, but they didn't. So let's see what we can do. How can we use these ideas to find, so we're trying to find the temperature at 25 minutes. It's not in the table. So what we can do is use the fact that if I find the integral of this, that's going to give me the temperature at 25 minus the temperature at time 20. Well, I can find this. This would actually be a calculator-based problem. So let's go over how to do this in the calculator. If I go alpha F2, there was our derivatives. This is our integrals. We're going from 20 to 25. Ooh, I better make sure my mode is good. It is. 20 to 25 of this function. So 0.4 square root of x, we'll use x just for fun, cosine of 0.06x, close parentheses, and it would normally be dt. Ooh, bad person, I forgot to put the dt. But in the calculator, we're going to use dx. So we're going to evaluate the change in temperature from 20 to 25 minutes. And I got 2.043. That's how much the temperature of the water changed in those 5 minutes. Well, I happen to know what the water temperature was at 20 minutes. That was given to me in the table. So all I really have to do is add this change to where I left off. So the temperature at 25 minutes is going to be 73.043 degrees Fahrenheit. The next example has to do with a pan of biscuits removed from an oven. So they were removed, and we're starting the timer as soon as they're removed. And as soon as they're removed, the temperature of the biscuits is 100 degrees. Oh gosh. Now the rate at which the temperature is changing is modeled by this, and it's a rate, so that's why it's a derivative. But the temperature would be just your B. So B of 0 is 100. The temperature at 0 minutes is 100. That'd be helpful to know. So first they asked us to find the value of B prime of 3. Well, that's just plugging 3 into that function. So I'm going to save myself some time and type that function into my calculator. E to the negative 0.173, and I'll use x instead of t in the calculator. Now to evaluate that function at 3, so I put in the derivative function into my y1, and then I'm plugging in 3. I get negative 8.236. Now what would be the units? Well, the units are going to be, it's the rate at which the temperature is changing. So it's degrees Celsius per minute. So explain what this means in the context. Well, it's negative, so we're decreasing, and it's the change in temperature. So this means that the temperature of the biscuits so I'm copying that straight from here, is decreasing because it's negative at a rate of, so since I've already said decreasing, if I put negative here, if you're decreasing by a negative, then you'd actually be positive. So we're going to put this is decreasing by a positive 8.236 degrees Celsius per minute. at time 3 minutes. Next it says sketch the graph of B prime on the axis below. So luckily I just put this function B prime in my calculator. So I want my window to kind of match their window. So this is -1, so I'm going to go with my x min as -2. This is 11, so I'm going to go all the way to 12. And counting by ones is fine. My y-axis, I'll go all the way to -7 and go up to +3, and it's counting by ones as well. So now I hit the graph. And if you wanted to be very exact, you could do the trace button and get you some good points. This one's about here. Let's go. See if we can find another good point. At 8, it's around -3. Around 10, it's at -2 point. So we've got this graph doing this number. Now, does this make sense? Well, some people would go, well, the temperature started at 100 degrees. Why is this graph negative? Well, remember, this is the graph of the rate at which the temperature is changing. So when you first take the biscuits from the oven, they are cooling at a faster rate than, like, after 11 minutes, they're almost at room temperature, right? Than after they have sat for a while. And the whole thing is negative because they're cooling the whole time. Your biscuits don't suddenly start heating up. Okay. The next question asks about the temperature of the biscuits at time 10. So they're wanting us to find B of 10. But I don't know how to do that. I don't have that function. I mean, I could try taking the antiderivative, but there's so much going on. Could we use the integral to find that? Well, we know the temperature at time 0. We know B of 0 is 100. We know what we started with. Could we find that amount of change from 0 to 10? How much did the temperature cool off between when we took it out of the oven and 10 minutes later? Well, I can find that. The integral of B prime from 0 to 10 is going to give me that change in the temperature at the end minus the temperature at the beginning. And since we have that function saved in y1, we can go alpha f2, go down to integral, and go from 0 to 10 of our y1, that is our derivative function. And with your calculator, it likes x. And it gives me -65.817. So that means the temperature has changed by -65 degrees. It's gone down by 65 degrees from the initial value of 100. So if I add 100 to this, I would get that the biscuits, so 100 minus 65.817, is 34.183. So the temperature at 10 minutes is 34.183 degrees Celsius. So integrals are very useful. Last example. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville during the first 5 days of a 60-day period. So during the first 5 days, 3 millimeters of rainfall has been collected. The height of the water in the can is modeled by S. The rate at which the height is rising is modeled by S prime. So find the value of the integral from 10 to 15 of S prime of t dt. So my first gut feeling is to put that function into my y1. So that I can take the integral of it very easily. 10 to 15 of the function I placed in y1 with respect to x. 11.159. Now what does this mean? This is actually finding s of 15 minus s of 10. This is finding the millimeters. So this is the change, amount of change in, let's see, the height of the water in the can. And then we're always doing this from one time to another. So from 10 to 15 days. So this changed over 10 to 15 days by 11.159. At the end of the 60-day period, what is the volume of water that has accumulated? Okay. So we really need to think about this. It's talking about the total from 0 to 60. But this function is only good from 5 to 60. So how in the world would I get what has changed before that in the first 5 days? Oh, they tell us that in the first 5 days we get 3 millimeters. So let's start over. So the change in the first 5 days, dt, is 3. Then we could find from 5 to 60 and then add them together. So this is something I could calculate with the calculator. So I'm going to take that 3, which is the first 5 days, plus the integral from 5 to 60 of s prime of t dt. And so you could actually just type that straight into the calculator. 3 plus the integral from 5 to 60, and we place that s prime in y1 dx. And we get 166.565. And this is the volume of water. This is the millimeters that the height has changed. Okay, so wait a minute. This was finding the height, the millimeters that have been collected. Oh, they tried to trick us. What did they actually ask for? Volume. Oh, no. Okay, so this was a cylindrical can, and it's been filling up. So at first it was like right here, and now it's way up at the top. So we know what the new height is of the water. We know the radius. Radius is 10, and we know our height. So the volume would be pi r squared times the height. Well, since I have the height in the calculator, I'm not going to retype it. I'm just going to go times pi times r squared. And I get 52327.899. It ends up being 0.9 millimeters cubed. Last one is a favorite for test questions. The rate at which people enter an auditorium is given by R of t. That's a rate. R of t is a rate. It's of people per hour. VIP tickets were sold to 100 people who are already in the auditorium at time 0. The doors close at time equals 2, so 2 hours later. If the VIP ticket holders stay for the start of the concert, how many people are in the auditorium when the concert begins? So we have our 100 that are already in there, plus the amount of people that have been added from 0 to time 2 of that, based off that rate. So 100 plus the integral from 0 to 2, and I'm just going to type in this function. Now you could have put it in your y1 if you felt like it, but since I'm only using it once, I'm just going to type the whole thing in, and we're going to use x in the calculator, and it tells me 1080. And that would be 1080 people have entered, these are the people that entered. These are the people that are already there. So it's 1080 people are in the auditorium. This is how many we've added over those first 2 hours, and these were the people who were already there.